When a user hits pay on a checkout, they expect immediate, flawless approval. To the end user, moving money seems as simple as loading a web page. In reality, processing that payment requires navigating three conflicting engineering constraints. First, the transaction must execute in under 50 milliseconds to avoid checkout abandonment. Second, it must comply with strict PCI and PSD2 security standards. Third, it must maintain absolute double-entry ledger consistency, guaranteeing funds are neither created out of thin air nor lost in transit. The naive approach to building this pipeline relies on standard web architecture, a single REST API server backed by a monolithic relational database processing commands sequentially. This structure collapses under the realities of a physical network. Dropped packets and mobile connection drops cause stalled requests, leaving the client uncertain if a payment actually succeeded. If you inject synchronous machine learning models into that same server to detect fraud, you freeze the main execution thread, completely missing the 50-millisecond latency window. And when volume spikes, thousands of simultaneous transactions attempt to update the same merchant balance. Relational database row locks trigger, throttling write speeds to a crawl. Achieving scale requires moving beyond standard CRUD patterns. To handle global volume, every phase of the transaction must be engineered as a decoupled, distributed operation from first principles. The most frequent failure in digital payments is the double charge. A client sends a POST request, the server executes the payment, but the HTTP 200 success response drops due to a network interruption. The client, assuming failure, automatically retries the request, triggering a duplicate payment. To prevent this, the client generates a unique UUID v4 string known as an idempotency key. This key is attached to the HTTP header of the initial request and all subsequent retries. The gateway checks its Redis cache for the idempotency key. If it exists, it returns the cached response. If parameters differ, like a changed amount, the gateway rejects it with a 400 error, preventing modifications under a stale key. This edge cache is volatile. Idempotency keys are typically evicted after a 24-hour time to live, and a Redis cluster can experience transient failures, allowing duplicate requests to leak through. The system requires a secondary, permanent fallback defense embedded deep within the core database. The central posting engine enforces a strict, unique check constraint on the idempotency key column of the payments table. If a duplicate request bypasses the gateway, the database physically rejects the insertion. Guaranteeing exactly once execution requires distributed concurrency controls, operating at both the volatile network edge and the immutable persistence layer. Once a request clears the API gateway, it carries highly sensitive raw card data. PCI DSS Level 1 compliance demands the strict isolation of the cardholder data environment to limit the surface area for a potential breach. The payload enters a vault proxy using format-preserving encryption. The raw card number converts into a randomized token, retaining its structure, keeping data off main servers. The tokenized payload travels synchronously to the fraud engine to evaluate risk. Accurate fraud detection requires computing complex features, like a user's transaction velocity over the last 30 days, or geographic distance between recent purchases. Attempting to query a database to calculate these relationships during a live authorization introduces unacceptable latency. The architecture solves this by offloading feature generation to an asynchronous event stream. In the background, an event bus running Apache Kafka constantly ingests raw transactional logs and user events from across the global network. A stream processor, such as Apache Flink, consumes these logs to continuously compute rolling risk aggregations. These pre-computed metrics are pushed to a low-latency, in-memory state store, ensuring the data is always warm and ready for extraction. During a live transaction, the synchronous machine learning scoring engine does not calculate anything. It simply queries the state store to fetch the pre-computed metrics, allowing it to evaluate the model and return a risk score in under 50 milliseconds. With a risk score calculated, the system navigates authentication. Under European PSD2 regulations, merchants must perform strong customer authentication. Executing this step successfully shifts the liability for fraudulent chargebacks away from the merchant and onto the issuing bank. The merchant SDK routes device data through the directory server to the issuer's ACS. The ACS combines this with fraud scores for real-time routing. Low risk triggers frictionless flow, approving instantly. High risk redirects users to verify identity. Modern protocol design transforms static security barriers into dynamic, data-driven routing problems that prioritize checkout conversion. After authorization clears, the architecture hits its final internal hurdle, the persistence layer. The financial state of the system must be permanently recorded in a double-entry ledger. This introduces database lock contention. When thousands of transactions simultaneously attempt to update a single aggregator's balance row, the database queues requests, paralyzing throughput. Wrapping standard SQL update operations in ACID transactions creates a performance ceiling that throttles high-volume throughput. You cannot rapidly scale a system that constantly locks rows to read and update balances. The solution is CQRS, physically separating reads and writes. The posting engine appends immutable journal entries to an SQL database, guaranteeing invariance without locking rows. It emits an event to Kafka, which downstream consumers process to update Redis balance views instantly. Global scale ledgers must abandon relational state updates entirely, relying instead on immutable, event-driven streams to separate the truth of the write from the view of the read. Viewed end-to-end, a payment request initiates cascading execution across the pipeline in a fraction of a second. These decoupled microservices interlock. The API gateway enforces exact execution. The vault isolates security scope. Async streaming enables sub-50 millisecond fraud scoring. CQRS eliminates database locks. However, recording a transaction internally means nothing unless you can programmatically prove the money actually settled through the external banking system. Post-settlement, the system ingests external bank settlement files, structured in global formats like ISO 2022 or BAI2 from acquiring partners worldwide. An automated reconciliation engine continuously consumes these files, matching external cash movements against the internal event-driven ledger locks to resolve discrepancies instantly. A global payment processor operates as a distributed state machine, engineered at every layer to anticipate, isolate, and seamlessly absorb failure.